Hello students, welcome back to the series Coordination Chemistry. This is the fourth module of the series. Here we study the stability of complexes. Stability of complexes, it means the complex exists and it can be stored for a long time under suitable conditions. That is, a complex exists and it can be stored for more time. That is, it has a stability, and it can be explained. The stability can be explained based on two types. In coordination chemistry, we discuss about two types of stability. It is thermodynamic stability and kinetic stability. So, two types of stabilities are there: thermodynamic stability and kinetic stability. And first, we will discuss about what is thermodynamic stability. It is a measure of the extent to which the complex will be formed or will be transformed into another species when the system has reached equilibrium. So, the thermodynamic stability, it measures how extent the complex is being formed. And now, here we have to consider, since it is thermodynamic stability, here we have to consider metal ligand bond energies, stability constants and thermodynamic variables derived from them. And it depends upon the reaction energy, and the stability increases with the increase in reaction energy. Here we refer complexes as stable or unstable. And then what is reaction energy? You might be knowing the reaction energy. See this figure, you can see that in this figure, this is a reaction progress, that is a reactant combined to form the products. You can see reactants there, they will be reacting to form the products, and there is an energy difference between the reactants and products, and the reaction energy is the energy difference between reactants and products. As the reaction energy increases, stability, thermodynamic stability increases. So, in the thermodynamic stability, it depends upon the reaction energy. Here we are considering, we are referring complexes as stable or unstable. Okay. Moving on. Second type of stability is kinetic stability. This refers to the speed with which the complex is formed, the speed with which the transformations leading the equilibrium will occur. Kinetic stability is all about the speed with which the reactants combine to form the product, and it merely depends upon the activation energy, and you might be very familiar with the term activation energy from the very lower classes. Actually, same you can refer this diagram. There you can see the reactants combining to form the products, and there is the peak position there. It is the activated complex. And what is activation energy? It is the energy difference between the reactants and the activated complex. So, that difference is the activation energy. As the activation energy increases, what will happen? It will be difficult for a reactant to convert to product. That is all clear to you. And now as activation energy increases, rate will decrease because reactants will be formed in a very less amount. It considers reactivity. For example, if we are discussing about the coordination complexes, it is all about the ligand substitution, etc. So, the kinetic stability will be dealing with the reactivity. And here complexes are referred to as inert or labile. In the case of thermodynamic stability, it was stable or unstable, but in kinetic stability, it is all about inert or labile. And what are inert complexes? Inert means it will be very inert, means it will be very difficult for the reaction to occur. So, inert complexes have large positive free energy of activation. And now, the electrostatic force of attraction between the metal and ligand makes the complex inert. See, if there is a greater electrostatic force of attraction between the central metal atom and the ligand, it will be very difficult to break the bond and form the new product. So, the electrostatic force of attraction between the metal and ligand makes the complex inert. If the force of attraction is very less, the complex will be labile. So, lability and inertness depends on the activation energy of the complex. And thermodynamically stable complexes may be kinetically inert or labile. There is no relation between a thermodynamic stability, thermodynamically stable complex should not be kinetically inert. It can be inert or labile. So, there is no direct correlation between this. Both are different. Thermodynamically stable complexes may be kinetically inert or labile. Here you can see three complexes examples, that is NiCN 4 times 2 minus, MnCN 6 times 3 minus and CrCN 6 times 3 minus. These three complexes all are thermodynamically very stable complexes, but the nickel complex is a labile complex, manganese complex, that is the second complex, is moderately labile, and chromium complex is inert complex. Okay. So, all the three complexes are thermodynamically very stable. First complex is labile, second one is moderately labile, and third is inert. And NiCN 4 times is thermodynamically, the first complex NiCN 4 times is thermodynamically stable, but you can say that it is kinetically labile. That is the irony. And in the another example, that is CONH3 6 times 3 plus, another complex. This complex in acid solution is thermodynamically very unstable, but kinetically it is inert. So, that is the difference between kinetic stability and thermodynamic stability. And now, while discussing about the stability of complexes, we have to understand what are chelates. See the figure, this is a figure, this is a lobster, right, crab, and you can see the central metal atom, that is copper. Actually, some ligands will be forming a ring like structure like this. These structures, when these structures are formed, the complex will be exceptionally stable. And chela of the lobster, that is a Greek word, chela of the lobster is referred to as the groups which function as two units and fasten to the central atom so as to produce heterocyclic rings. So, a ring structure is formed by some groups, and such ligands will be polydentate ligand. Then we have discussed what is a polydentate ligand in the previous classes. Polydentate means more than one donor atom. So, since they contain more than one donor atom, they will be bound to the central metal atom, forming a ring. So, a polydentate ligand can form complexes with ring structures when the donor atoms in these ligands are directly attached to the same metal atom. And such ring structures, such ring structured complexes are called as chelates in coordination chemistry, which is very important. And these chelate complexes are having a strain free ring structure. Since they are forming a ring structure, but these ring structure are having no strain. So, that is why they are called as strain free ring structure and are formed by two or more donor atoms. I have already told that polydentate ligands are forming such structures. And the process of formation of a chelate ring is called chelation. So, what is chelation? It is a process of formation of a chelate ring. They are more stable than the non-chelated complexes of the same metal atom. When we compare a metal atom, same metal atom is present and one is forming a complex with a ring structure, that is chelate, and another is forming a non-chelated, that is open chain structure. Which one will be stable? The chelated complex will be highly stable. And this chelate complexes, the rings formed by this chelates, the rings formed in this chelates may be 5 or 6 membered, usually 5 or 6 membered. And these are the examples for chelating ligands, that is ethylene diamine tetraacetic acid, EN ethylene diamine, DMG means dimethyl glyoxymato ligands. These are the example for chelating ligands. And here you can see the structure of ethylene diamine tetraacetic acid. See the structure. you have how many donor atoms are there in the ethylene diamine tetraacetic acid? We have studied that this EDTA is a hexadentate ligand. Then how many donor atoms are there? It is 6. And how it is 6? That is, we can count the donor atoms. You have 2 nitrogen, right? 1, 2, 2 nitrogen atoms and 4 oxygen atoms, 1, 2, 3 and 4. So, 4 plus 2, 6. 6 donor atoms are there in the ethylene diamine tetraacetic acid. Thus, it will be forming a ring structure. And the second example is ethylene diamine. It can be denoted as En. And how many donor atoms are there in En? There are 2 donor atoms, that is 2 nitrogen atoms. And these 2 nitrogen atoms will be attached to the central metal atom to form a ring. And now you can see the way in which ethylene diamine is forming a ring structure. This is the structure of ethylene diamine. Ethylene diamine means ethylene diamine, and on the whole it will be forming a ring structure with the metal complex, and you can number the ring. It is a 5-membered ring, right? 1, 2, 3, 4, 5. It is a 5-membered. I have already told that these chelates will be forming 5-membered or 6-membered ring. And now this is the metal EDTA complex. You can see the central metal atom at the center of the octahedron. This is the central metal atom, and ethylene diamine, the single ethylene diamine ligand will be forming this structure, because EDTA is a hexadentate ligand. So, there are 6 donor atoms and 4 oxygen atoms plus 2 nitrogen atoms. You can see I have already counted there 1, 2, 3, 4, 5 and 6 donor atoms. So, this is the way of forming chelate, metal chelate complex. And this chelate effect, that is, chelates are highly stable. I have already told that metal chelate complexes are very stable, exceptionally stable. And what is the reason for this exceptional stability? It can be explained on the basis of thermodynamic functions. You know, while considering the thermodynamic, you have studied this thermodynamics in the physical chemistry classes. There we have considered different aspects, different terms you have studied, that is enthalpy, entropy, free energy, etc. all will be discussed here. Consider the 2 reactions, that is a cadmium complex, cadmium water aqua complex, CdH2O 4 times 2 plus. The complex is reacting with the methylamine. The ligand is, this ligand is the methylamine ligand. It is a monodentate ligand, because 1 nitrogen atom is there. It is a single donor atom. So, cadmium aqua complex is reacting with the 4 molecules of methylamine to form cadmium methylamine complex. The water molecules are replaced by this methylamine ligand, and the reaction is like this: CdNH3 twice 4 times 2 plus 4 H2O. That is the first reaction. And consider the second reaction. The second reaction is all about the same complex is reacting with the polydentate ligand, that is ethylene diamine. It is a chelating ligand, I have already told, and that is reacting with 2 molecules of ethylene diamine. Why 2 molecules of ethylene diamine? We know that ethylene diamine is a bidentate ligand. 1 ethylene diamine molecule will be containing 2 donor atoms. So, 2 ethylene diamine molecule is needed instead of 4 methylamine in the first case, and 2 ethylene diamine molecule will be reacting with to form CdEn twice 2 plus 4 H2O, and this is the 2 reactions. And now, in the first reaction, delta S0 means, delta S0 means it is a change in entropy of the first reaction. It is 0. How it became 0? See this? First reaction, how many molecules are reacting? 1 molecule of this complex is reacting with 4 molecules of this ligand, 4 plus 1, 5. And the reactant side, you can add the number of molecules. the complex formed is one molecule of this complex is formed. How many water molecules are formed? 4 molecules. So, here also you have, you can number the number of molecules on the left hand side and right hand side. It is 5 here, it is also 5 here. How it becomes 5? 4 plus 1, 5, 4 plus 1, 5. So, 5 molecules on both the sides. 5 minus 5 is 0. That is why delta S0 in this case, in the first case you have delta S0, 0. But in the second reaction, delta S0 is positive. How it became positive? Let us have a look at it. See this, the second reaction, number of, you can count in the number of molecules. It is 1, 1 plus 1 plus 2. 2 ethylene diamine molecules are reacting. 2 plus 1, it is 3. And now how many molecules of the products are formed? 4 plus 1, that is 4 plus 1, that is equal to 5. So, you have to minus. What is the difference? 5 minus 3. 5 minus 3 is 2. 2 is the entropy. Change in entropy is positive in the case of second reaction, but in the first reaction it is 0. So, delta S0 in the first reaction is 0, in the second reaction it is a positive quantity. And now you may be knowing this famous equation in physical chemistry, that is delta G equal to delta H minus T delta S. Delta G is the change in free energy, delta H is the change in enthalpy, T is the temperature and delta S is the change in entropy. And we have seen that the delta G, we know, you may be knowing that delta G, as the value of delta G is negative, the reaction will be spontaneous. So, for a spontaneous reaction, the value of delta G should be negative. And when we compare both the reactions which we have discussed in the previous slide, it was found that delta H is negative for both the reactions. Now, what is the determining factor for the value of delta G? It is temperature and delta S. And if we are keeping the temperature, if we keep the temperature of both the reaction constant, it will be delta S the determining factor. In the first reaction, delta S is 0, then the whole quantity, this whole quantity will be 0 in the first case, and delta G will be merely depending upon the delta H value. It is negative in the first case. Okay. And now, in the second reaction, this delta S is a positive quantity. As a delta S value is a positive quantity, the whole thing will be positive, and but there is a negative sign here. So, the whole and this whole thing, this whole value will be more negative if the delta S value is a positive quantity. And so, in the second case, we have, since delta S0 is a positive one, the second reaction will be having a higher negative delta G value. That is why the reaction for a chelating complexes will be formed spontaneously, and they are very or exceptionally stable. That is the point. And now, we have to consider two types of stability constants while studying the stability of complexes. They are stepwise stability constant and overall stability constant. From the name itself, first one is it is merely connected to the stepwise in each step. It is the stability constant of each step, and the overall stability constant is all about the overall reaction, stability constant of the overall reaction. And according to Jerram, formation of a complex in aqueous solution proceeds through a stepwise formation, stepwise fashion with corresponding equilibrium. And you can consider the different steps involved in the formation of a complex. See, the complex formation, suppose if the complex formation takes place in several steps, this is the case. First, a metal will be combining with a ligand to form MLN, and that is, in the first case you have the stability constant, that is K1 equal to concentration of ML by concentration of M into concentration of L. That is the first step, that is the case in the first step. In the second step, that is once the reaction MLN M plus L giving Ml2. If it forms Ml2, the stability constant is K2, that is K2 equal to Ml2 divided by M, concentration of M into concentration of L. And now Ml2, this Ml2 when combined with another ligand Ml2 plus L, it will be combining to form Ml3, and in that case K3 equal to concentration of Ml3 divided by concentration of Ml2 into concentration of L. Generally the reaction can be represented like this: Ml n minus 1 plus L giving Mln, and this in this case Kn can be written as concentration of Mln divided by concentration of Ml n minus 1 into concentration of L. So, in all the cases the equilibrium constant in each step is called the stepwise stability constant. That is, in each step you have the stability constant. These are the stability constant 1, 2, 3, these are all the stability constant in each step. So, they can be called as stepwise stability constant. Okay. And now, thus K1, K2, K3 etc. up to Kn can be called as a stepwise stability constant. But if the complex formation is considered as a single step, or if a complex formation take place in a single step, it can be represented like this: M plus NL giving MLN. And in that case the stability constant can be written as beta n equal to the concentration of MLN divided by concentration of M into concentration of L. This beta n is called the overall stability constant, because it represents the stability constant of an overall reaction. If we are considering the formation of that complex in a single step, the stability constant is beta n. And this beta n can be related, beta n and this K1, K2 etc. are related by beta n equal to K1 into K2 into K3 into etc. up to Kn. That is, the overall stability constant and stepwise stability constant can be related like this. This is the way to write. And now we are moving to the different factors that affect the stability of complex. See, the stability of complex means we have discussed two types of stability and everything, and now the stability of these complexes will be depending upon several factors. One by one will be discussed. Number one is environmental factors. Environmental factors means this includes temperature and pressure. Of course, temperature of a reaction will be very crucial, temperature and as well as pressure in each reaction, whether it is a coordination complex or any other organic compound or inorganic compound, anything, the temperature and pressure will be a determining factor. So, number one, first factor is the temperature and pressure. As the temperature of the reaction increases, you can see the stability is decreasing. The reaction, there will be, if we are providing some temperature for a reaction, that system will be gaining some energy to the bond break, for the bond breaking, for the metal ligand bond to break, it will be attaining some energy and that bond will break. Of course, that bond will break easily. So, one of the determining factors temperature and another is pressure of the condition. And now the second factor is the nature of the central metal ion. That is, we know coordination compound or coordination complex is having a central metal atom and ligands. So, second determining factor is the nature of that central metal ion. And in the nature of the central metal ion, first one is the ionic size, second ionic charge, and the outer electronic configuration of the central metal ion will be the determining factors. First is ionic size, ionic charge and outer electronic configuration. And now you can discuss one by one. As the ionic size increases, the stability decreases. So, for a stable complex, ionic size should be very less. For example, zinc Zn2 plus forms stable complex when compared to cadmium 2 plus. You may be knowing the size of these complexes: zinc, cadmium, mercury. This is the way of the arrangement of these elements in the periodic table. You know, zinc is at the topmost, coming down you have cadmium, and the last you can see mercury. So, the element which is in the upper side, or the top position, the element which is on the top position will be having lower size, less size, and Zn2 plus, this Zn2 plus will be very small when compared to cadmium 2 plus, this cadmium 2 plus. So, zinc will be forming a stable complex since the ionic size is less for zinc. Now, the second factor is, second thing in the nature of ligand is the charge of the central metal atom. As the charge increases, stability also increases. Charge means you are given the examples here. In this case, it is lanthanum 3 plus, it is having a charge of 3 plus, strontium is having a charge of 2 plus, and potassium is having a charge of 1 plus. So, which is having larger charge, you know, charge is more in the case of lanthanum, it is 3 plus. So, lanthanum 3 plus will be forming stable complex, that is why the order is like this, lanthanum 3 plus which is having a greatest stability. And now, next is the nature of ligand. So, first one is the environmental factor, that is temperature and pressure, second was the nature of the central metal atom, and the third is nature of ligand. In the nature of ligands, first one is size and charge. Size and charge of the ligand also will be very important. Ligands with high charge, that is more charge, and small size are forming stable complexes, or ligands with high charge to size ratio will be forming stable complexes, which means that the ligands should be having high charge and small size, as in the case of central metal atom also. And the second factor, in the case of ligand, the ligand should be more basic, that is basic character of the ligand is also very important. The ligands with high basic character will increase the stability of the complex. That is, aromatic diamines forms unstable complexes, while aliphatic diamines will be forming stable complexes. You know, this aromatic diamines are less basic than aliphatic diamines. That is why aliphatic diamines are more stable while forming the complex. The ligands like CN, NH3 etc. will be forming stable complexes because they are having very high basic character. So, as the basicity of the ligand increases, the complex will be very stable. And now the ligand concentration. Concentration of the ligand is also a determining factor. As the concentration of the ligand increases, stability will certainly increase. So, if we are having in a reaction mixture more concentration of the ligand, then that complex will be very stable, because more and more ligands will be combining to the with the central metal atom to form the stable complex. And now, fourth effect is the chelating effect. Chelate, we have already studied what are chelates, what is chelation, etc. So, this chelating effect is also a very important factor in the formation of a stable complex. Multidentate ligands forms stable complexes than monodentate ligands. We have already studied, and how it is can be explained on the basis, we have already explained the phenomenon using thermodynamic functions etc. And that is why the chelating ligands are more stable when compared to the monodentate ligands. And the chelate formation will be depending upon the ring size. As the size of the ring, this 5-membered rings will be very stable when compared to the 6-membered ring, and least stable will be therefore the 7-membered ring. So, you have to keep in mind that 5-membered ring will be very stable compared to 6, and if the 7-membered means the size is increasing, the ring size is increasing. As the ring size increases, the stability is decreasing. Okay. And now, it depends upon the number of ring. If the number of ring increases, as the number of rings increases, stability also increases. As the size increases, stability decreases. As the number of ring increases, stability will decrease. Stability will increase. As the number of ring increases, stability will increase. And now, fifth factor is the effect of substitution in the ligands. This if the substitution in the chelating ligand will decrease the stability of the complex. If the substitution increases, there will be steric strain. So, the effect of substitution on the chelate will be very determining factor or very important in the case of the stability of complexes. That is, bulky groups will decrease the stability. And now we have another effect, that is macrocyclic effect. What is macrocyclic effect? That is, end-endate macrocyclic ligands give stable complexes than end-endate end-endate open chain complex ligands. That we have explained in the chelating effect, because thus macrocyclic ligands mean they are form a cyclic ring structure, and in the case of open chain complexes, the thermodynamic factors will be affecting, like the delta S, the value of entropy, change in entropy will be increasing in the case of macrocyclic ligand when compared to the open chain ligand. That is the macrocyclic effect. And these are the factors that affect the stability of complexes. And we in this module we have studied different types of stability, kinetic and thermodynamic stability, what are the differences, and we have studied what are chelating complexes, what are chelates, what is the process of chelation, what is chelation, etc. And two types of stability constants was discussed, overall stability and stepwise stability constants, and finally we studied what are the factors that affect the stability of complexes. And thank you for watching this video. In the next class, we will be discussing about the theories of coordination compounds. Bye.